では、OK, so my name is Takaharachi from TMU. So this is my from my recent work. I'm talking today about synthetic filtrations, which is it's of course the filtrations in the sense of the probability theory. And this is new because of this word synthetic. So I explain this one. Okay. So now, say if we when we think about the past, then we look back the past. We usually think about our past is from our birth point. This is a past toward to the present. So there is some single path. So it's just like this guy. All right. So from this is birth point, and we are here. So this is a usual our feeling about our past. And then from now on, we are expecting to the future is expanding to towards the uncertain future. This is our image, usual image. But this talk, I doubted this model. And instead of that, we are some symmetric one, which is this guys. And there are lots of the past toward to now. And the now is a synthesis of this many possible pasts. But because of our limitations of our perceptions, we only see this many paths by some projections into the one single path. This is our observation right now. I'm feeling. So, in a one sentence, I think it's this single path past is just an illusion, and the reality was like this. So this based on this image intuitions, I'm talking today's talk. I'm making today's talk. Okay. So this is the outline, starting from the time domain. Time domain is essential for this talk because it's a time domain is not linear in this case, because there are lots of the past against today. And this time domain, and with this time domain, we define a filtration. Actually, this is not the new one. It's a collaboration with the Professor Liu and Professor Nakajima, and but I because for the beginners or the unfamiliar people, I will explain some about this filtration. And then move on to some tools which are borrowed from the algebraic topology and for making our time domain today. Okay, and then this is actually this category sigma is a key concept of today's talk, and it represents our time domain according to our intuition. And then the filtration, sigma filtration is the probabilistic filtration over this category sigma. And then next, we make some analysis, with homological analysis of this sigma filtration. The final one is providing some concrete model of the sigma filtrations, which is a Dirichlet filtrations. And using from that point of view, Dirichlet filtration point of view, we see what the Bayesian update is and some final conclusions. Okay. First, I will start with the time domain and filtrations. Our analysis is based on the category theory, and the category is, as you know, it's consisting of two entities. One is the object, and the other one is arrows, which are in between those objects. And we need the category of probability spaces. Okay, so the natural is objects of category of probability space, which we denote prob. is of course a probability space. So but the arrows in between them matters. So I explained that. Let X and Y be two probability spaces with okay, omega is of course underlying set, and f sub x is a sigma field, and p sub x is a probability measure whose domain is f sub x. Similarly, y. Okay, we use this notation throughout today's talk. And we have the measurable phi, and the phi is called a null preserving if this equation holds. This is the absolutely continuous, so which means if the py something is 0, then this one is also the 0. And in other words, it preserves the negligible events under push-forward measures. And also, I note that if we have the equality in here, then it is the phi. It means that phi is a measure preserving. This is a stronger concept. This talk I don't use, but use it. But for some intuition, it is helpful. It helps. Okay. Then we make a category which is prob, whose objects are all probability spaces, and the arrows are null preserving maps between them. All right. Okay, with this with this probability, I'm sorry, category prob, we define the T filtrations. T filtration, the T where T is a small category, and which is considered as a time domain. What is small? Small categories. Small categories not so important in this talk, but it means that category is described in the set theory, within the set theory. So all objects, set of class of all objects is a set, or all arrows are set, or something like that. So we can talk in a usual set theory. And now the T filtration is a contravariant functor f, which is from the time domain T to the probability category probability space prob. And the functor is a kind of function between categories. So here is a category T, and here category prob. So we have the function like the things which is a functor f. And we have the STU, these are objects of T, which means these are time. This represents a time, STU. And in between S and T, we have the I. This is this means a development way, or the evolution of time. This represents the evolution of time from S to T, and J as well. And then we have the composition J circle I. This is evolution from S to U via T, okay? And then F maps these guys. So because the functor is a function type, function in between categories, and which preserves all the fundamental structures of categories. So S is maps to F of S, and the T maps F of T. But these are objects of prob, which means Fs or Ft are probability spaces, okay? And in between them, we have the Fi, this one, is an image of I, and it's a map. But the Fj as well is a image of J. And the point is, you see that the direction of arrows are opposite. Here, for T, it's downside, but for prob, it's upside, so it's opposite, and that is why we use the word contravariant. The contravariant functor is changing the direction of arrows, but that's it. And here OP is also the opposite directions. Okay, and this is a filtrations, and we can see this T filtration is a generalization of the usual or the classical filtrations, but why? Okay, if we have the classical filtrations, this is a filtered probability spaces in a classical sense. So among that, of course, this FT is filtrations. Then from this we can define our filtration F, which is a contravariant factor from T to prob, by the following way. Because of the classical filtrations, the time domain is just alphas, or the set of real numbers, positive real numbers, and these STU are real numbers representing time. Okay, and future is in these directions. And then we can think in general that any partial order, this is total order set, but any partial order set or pre-ordered set can be seen as a category. There's a general way. How do that? So we constrain T with that general way, which is called the IOD. Okay, so now in this case, we have the object. This is T. T is a category, so they have their objects is STU. They are same of the original R's members. Okay, but the arrows is here. This guy, star SD. There's a unique arrow from S to T, which is star SD. If and only if S is less than or equal to T. Okay, so in this way, we can think of we can make a category T, because of this identity arrow is represents to the reflexive relation of the original total order set. S is less than or equal to S, of course, right? And then this composition is a transition rule of the transitivity of the original total order set. So in this way, we can make any partial order set becomes make a category. So we get T. Then the remaining is how to build this filtration F, which is a functor. But say that for time S, we have the probability space F of S, and then we define F of S as this triples. The underlying set omega is the same of the original classical filter, original omega. Okay, so this is this, right? And then how about the sigma field, which is F sub S? So F sub S is taken from the this filtrations, or the original classical filtrations of at time S. And then the probability measure P is the same P, but it's of course restricted to the domain, whose domain is restricted to the F sub S. Okay, so in this way we can think about the we can define the probability space. Then what is the arrow? So but we need to define the arrow mapping arrow. So the F of star ST. We simply define these guys be the identity arrow over this underlying set omega. Okay. Then the remaining is we need to check this one omega in this is a measure preserving. But in order to check the one's measurability, we only need to the thinking about the inverse, and then and this is which is now the well defined. So that is a point. But however, this Fs and Ft are taken from the original classical filtration, and also the S is less than T, so which means that Fs is a subset of Ft. So this the inverse of identity must be embedding, because of the Ft is a bit bigger set than including the Fs. So it's well defined. Okay, so in this way that we can make any classical filtration be our T filtrations. All right, so this is a general thing. Okay, now we are moving to the explaining about some fundamental tools taken from the algebraic topology, which is a simplex category and others. The simplex category is a category delta, okay? And then whose objects are this finite ordinals, bracket n, consisting of the integers 0 through n. So the number of elements of bracket n is n plus 1, okay? And then naturally this bracket n is a totally ordered set, okay? So, and then we define the allows from bracket n to bracket n be any order preserving map f from the partial order set M to the partial order set N in bracket. Okay, so this is then of course this can be this will be a category, and which is called the simplex category. The very fundamental concept in the algebraic topology or algebraic geometry. Okay, because we have many allows from the bracket M to bracket N, but there are two special types of these allows, and one is the little delta, this guy, and the other one is little sigma, and the little delta is enlarging one dimension up, so from n minus each bracket to n bracket, so the one dimension up by adding adding some missing part is here. But anyway, I'll explain that in the example soon. And it's on the contrary, the sigma is decreasing dimensions from n plus 1 to n. Okay, so it's a different. But so I explained the detail by an example. This is a set, okay, finite sets. Bracket 3 consists of from 0, 1, 2, 3, okay, the 4 elements. And bracket 2 is a 0, 1, 2, 3 elements, okay? And this sigma is defined by like this. Here, the important thing is that this subscript 2, which means we duplicate the allows at the target 2 here. So it's duplication there is. From coming from 2 and coming from 3, we duplicate 2 allows. So this is a sigma 2, 2. And sigma 1, 0 is similar. 1, 0, so 0 means we duplicate at 0.0, so which is, it's like this. The other maps are, of course, the identity. And then on the other hand, we have the delta here. So delta 2, 1 is at 1, we vacant at 1 here. So at 1, we don't have arrows, incoming arrows here. So in this way, every arrow in the simplex category, delta, can be represented as a composition of these sigmas and deltas. Okay, so this is very important because when we need to think about the all allows of the delta, we only need to think about these deltas and sigmas because the other maps can be constructed with composition. So this is very convenient properties for the simplex category delta. Okay, the simplex category is a kind of the just bone or the skeleton. But we need some, upon that skeleton, we need some, continuous something, or like a meat or those stuff we need. So, or concretely speaking, we need some topological space, which is a concrete representation of the each n bracket or something. Okay. So for n, we specify the topological space delta n, which is a instantiation of the concrete example of the bracket n. Okay, this delta n is a subspace of the Euclidean n plus 1 dimensional Euclidean space R n plus 1. Because this is a vector space and finite dimensional vector space, we have the basis vectors E0 to En. So n plus 1 usual standard basis, which is a 0, 0, 1, 0, 0, 0, and 0, 1, 1, 0, 0, 0, or something. Okay. And then this delta n is defined as a set of the all all linear combination, but convex linear combinations spanned by these bases. So here, the Wi is a coefficient, but those are the in between 0 and 1, and the sum of all is 1. So it's just a convex subset of the Rn plus 1. And then, so the naturally this delta n has a topology, which is just a derived topology of this Euclidean topology in defining Rn plus 1. So this is a topological space. And we call this a standard n simplex. For example, delta 0 is just a 1 point, okay? And delta 1 is this segment, line segment from 0 to 1, okay? And delta 2, which is, of course, is a subspace of R3, is a triangle. And then this is and for delta 3 is a tetrahedron. It's a Shimentai. Okay. So this is the sequence of the topological spaces, and then we will use them as the underlying sets of the time evolving probability spaces. So we will think about the sequence of probability spaces, and each probability space has this delta n as a underlying set, which we usually say that omega. Okay. So this is very important. Now so we have this simplex category to the topological space. There is some correspondence we specify, which is to n bracket. We specify the delta n, but we want to make this correspondence be functor, and the resulting functor is R0. So in order to do that, we need to define the arrow part. So we defined the object correspondence, but have not yet specified the arrow part. So more concretely speaking, because all the simplex categories arrow comes from represented as a composition of this little delta and little sigma. So all we need is all we need to define is what are the corresponding maps of delta and sigma, and this is we call the D and S. Okay, so the delta is mapped to this guy, and the arrow direction of arrow is now opposite because it's a delta OP to top. Okay, it's an opposite contravariant factor. And then we define this DI and DSJ be like this. I don't go into the detail of this definition, but this is a very, very natural way. And we call this the standard geometric realizers R sub 0. Okay. I don't go into it, but if you have time, just please check it. Okay, now I'm going to explain our main structure sigma, which will use for representing our time structure, which is the present is a limit of the possible many past. Okay, time in the context. This is our original concept. The set of the time in context is okay. So there's a word context, and context, the set of context is denoted by sigma 0, and sigma 0 is defined as the product of the all bracket T. So it's like this. Okay, So the any element, taking any element C from sigma 0, then the C can be written this like this C0, C1, C2. And each C0, C1, C2 is a member of this zero bracket, one bracket. So they are in general, the CT is an element of the bracket T. Okay. And we call this context. Why this is called the context? Well, I will explain soon. Then upon this sigma 0, set sigma 0, we introduce binary relations, sim-t. And the two contexts, C and C dash, is in the relation of the sim-t if and only if um, up from T and beyond, those two contexts coincide. Okay, so this is two simplex, but at time T, it's meet. This is C and this is C dash, and so this kind of situations that happen, then C and T, C dash is equivalent with these relations. Okay, and obviously that this relationship is equivalent equivalence relations. So we can think of the quotient or the class equivalent class of C, and using that we defined new notation T bracket and sub C. And we call this a time T in the context C. So it's close to T, but with context. So that is this subject, time in a context. And it's a pair of the time and also the context. But it's a quotient of, so the equivalent class of context. Then we define a set sigma. Again, I'm sorry, there is some confusion about delta or sigma. There are many deltas and there are many sigmas, but we slightly change the font. But this is a sigma is a okay. It's a set of the all time t in the context C. So the point is so different contexts encode the different parts. So this is if this is now, okay, this is now. We see the past. There are lots of the past, but it is represented by. They are represented by the context, different contexts. Okay, so this is a idea. For example, okay, there's an example, a good figure for this is a example of this object. So time 2 with context C, where context C is a sequence of these guys. Then context C here is because of the we need this guy. So this is a equivalent class of belonging this context C, but with relations sim2. So that means from time 2 it coincides. But the other the past we have the many possibilities. So it's like this. So this 2 is remember this guy is like this. The this two bracket is like this. So or this is of course the realization, but we can see this is a triangle and we have these are three faces. So each edge corresponds to each faces. These are face. Okay. So for each face is has a structure one bracket, and each one bracket has a zero faces, which is a vertex of these lines. So in this way, we can so we have these structures because of the corresponding to these guys. So here these ones are different one, but has the same structure, have the same structures, and similarly these guys. The usually is we only have the one zero bracket or the one bracket, but because we have our time is depending on context. So it's, depending on context, we have the many zero bracket or one bracket. But from two, we only single pass because of the this is two C is after time two, the order context belonging this guy is the same path, has the same path. So this is an image of 2C. And it's very similar to our original intuition of the, okay, so this is now, then the current present is, the limit of the many possible past. Okay. All right. So we are making the category sigma, which the two objects is this kind of the two sub C or this time with context. And the arrows in between T and T dash C, we have the dropping the context and the T bracket, T dash bracket. So these are the just delta complex. I'm sorry, simplex, delta simplex, the simplex category, delta, the arrows of simplex categories. So which are the, just represented by the composition of little delta and little sigma. And then, but it's in this case that the C or C dash is meet somewhere, but it's C and C dash is at least here T max of T and T dash plus one. From that point, it's coincides. Then we can have these guys. If not, it's a different, very different syntax. I'm sorry, context. Then the in between those guys, there's no arrows. So it defines as some if C and C dash has a parents and children relation, those stuff, then we have this set of the arrows, and this is a sigma. Then naturally we can define the new functor U sigma delta, which is a forgetful functor from sigma to delta. Forgetful means in category series just to forget some structures, dropping some structures. In this case, context. So the dropping context. So okay. And also we simply write these guys. It's coming from the original. These guys it's in the simplex category delta, and here is of course it's from sigmas, but we a little bit the confusing way, but adding some context C dash, we use these guys. So the important thing is that all the arrows in this sigma can be represented with this little delta and little sigma maps. Again, just like the simplex category. And this is a category sigma, and we will use this guy as a time domain. Okay, so this is an image. So we have here tomorrow. I'm sorry, today we are here. So we have this the cone towards the past. We have cone, but tomorrow we will step up, and then we have another cone which will be expanding like this. Then this part is a new part. Okay, new space which is converged to but tomorrow, but today we don't know that. And the black swan will live in or lives in this yellow part, and that's why today we don't see black swan, but tomorrow we observe that black swan. Okay, so this is okay. COVID-19 was not known in 2019. But 2020, suddenly we observed the black swan, which is COVID-19, this kind of image, okay? And also different image, this one. So the future is here. But we are here, this now. But with this future, which is a one dimension up, but this future is consists not only us, our now, but the another now, or yet another now, as converges and making the future. Okay, this is the image. So the future is not only coming from us, our future, our now, but it's a gathering which we have not seen, but some may include the black swan. Will gathering and making a future. This is the image. Okay, so I'm not sure that you guys can use this idea, new intuition to your theory, but let's discuss later about that. Okay, and the sigma filtration. Now it's a filtrations. Go back. You remember the sigma filtration is a time domain to the functor from time domain to the prob, which is a category probability spaces. And then we have the X is filtrations. Then it must, we have the following diagram commute. Here X, this is filtrations, and this is a forgetful functor from sigma to delta. So it's a dropping the context. And then because we have the standard the realization, so say here the n bracket, then we have the delta n, which is remember that this is a convex subspace of the Rn plus one. And then because this is a topological space, we can make this measurable space by the any topology O from this is topology. We can make a Borel sigma field containing O. This is a smallest sigma field containing the original topology. So in this way, we can make these guys to be a measurable space. So this is a measurable space coming from the say n bracket, and then we have the from probability space to measurable space. It's another forgetful functor, but in this time, though, just dropping these guys probability measure, just dropping probability measure, then it will become a measurable space, of course. And then so basically this commutes. We only think that the situations this commutes. Okay, and we use the word sigma filtration if this factor x satisfies or the x commute making this diagram commute. Okay, now we define the sigma filtrations. Then we just make some small analysis, the homological analysis over there from them. The idea is like this. The categorical constructions of the sigma filtration describes how probabilistic information flows through the contextual time. So we have the time with the context, and if we can define the information flow over that time. So it's not a linear time, but it's from the past from many parts the information comes and it converges now. This kind of we can define. However, the structure of the flow itself possesses the internal consistency and the obstructions. So sometimes it's smoothly flow, but sometimes there's an obstruction and blocked by some. We can think this kind of situations, and then it's much like a topological structure of a simplex category, simplicial complex, not just simple information flow. So to capture these situations, say that some obstructions or stuff, we need in order to capture those stuffs, we can use the algebraic method, and we don't use a homological framework for sigma filtrations. The homology is a tool in the algebraic topology, and then it is used for the representing the obstructions or the say holes in the in the ball there is a hole, then it becomes a torus or those stuff. Okay. In the financial concept, we have some obstacles. We see some small obstacles. So breaks some martingale properties, or we have some arbitrage. We can make some arbitrage trading, those stuff. This is breaking some consistency, or maybe there is some hole, those stuff. So I'd like to express this kind of things in a algebraic way, and the tools is now homology. Okay, and here so capturing making homological structures, we need some structures, and we use which is bounded operator. Boundary operator is necessary, and so this important boundary operator is created through our conditional expectation. And there, a compositions revealed how information coheres, or fails to cohere. So across these contexts, because we have many contexts. Okay, so I will explain one by one these situations. So before going forward, we need to review our conditional expectations. This is probability space, but in this case, our conditional expectation is not only inside one probability space, but we have the two probabilities x and y, and there is a null preserving map phi from x to y. And then for every random variable f on the probability space x is moved on to the another random variable y. I'm sorry, if e phi f, which is a random variable defined on the probability space y. And we write this guys e phi f, and it has a property like this. So this final statement is very similar to the traditional conditional expectation formula, except this guy's phi inverse b, and because of the in the classical sense that the conditional expectation is only defined on the same probability, one probability space, but ours is on the different conditional probability space, which are the x and y. So we need to changing the measurable set. We need these guys phi inverse b. But anyway, so this is a generalization of the classical filtration. So if the x and y coincide, then it's nothing but the classical conditional expectation. So it's a generalization. Okay, so use this conditional expectation to make more, but the conditional expectation is just a 1 point, but can be think as a functor, because the conditional expectation satisfies the Tower property like this. So it's corresponding to this corresponds to the composition in a categorical sense. So which means that we preserve the composition or the functorial way. So we have we can define the functor E, which is coming from the category probability spaces to the Baraha space, categories of Baraha space, which are corresponding to all the random variables defined on that probability space. So the L1x is a set of all random variables defined on the probability x. Here, the random variables, the target is now in the limit is fixed to the R. But so L1x is f is x to R. So we fix these guys, but it's not without generalities we can define. Of course we can generalize these guys, but currently we just fix R. And then from the random variable f defined on the probability space x, we have the conditional expectation, the corresponding conditional expectation, but it's defined on the random probability space y, like this. So So in this way, we can make a functor representing the conditional expectation, and we call this a conditional expectation functor. To use this guy, we define the boundary operator. So boundary operator delta TC is now the CTC is just an anonym of the random the set of random variables, which is this guys. But the XTC is you remember X is filtrations, and the TC is inside here. We have this is a time with context, and each time context we have some probability spaces, and yes, that is this guy. So on this is a probability space. So over this probability space, we have the set of the random variables, which that is this CCT. Okay. All right. So now CCT. See here the two. So T and T minus one. So it depends on the context. So we have the superscript C, which is some fixed context. And then from the future to now or something, we define the boundary operator. The boundary means that remember that we have if this is a T2 delta 2, and we have the three faces, and we have the projections to each faces, right? So this is this. So using these projections, we make this map, boundary map. These guys, this is a boundary of the triangle, right? So the three edges are the set of union of these three edges are, of course, the boundary of the whole triangle. So this is a triangle map is coming from the CT2 to CT1, and is defined by the sum, alternative sum of the conditional expectation to each faces. Okay, so if we have here, then this is a conditional expectation projection, and this is also projection. This is so these 3 points. We have an alternative sum. So the minus one, I. This alternative sum is very natural in the algebraic topology. Say that if you think about the very one of the oldest theorems in the algebraic topology, which is Euler's theorem. You think about the number of the points and number of edges and number of spaces. We have the faces. We can compute the something minus something plus something. That is called the Euler number, and that characterizes if this graph, some graph has a circle or not. This kind of thing. Not circle. I'm sorry. There is some way of at walking all the passes without duplication. Those stuff. So this is a very this number will represent some invariant characteristics of the whole structures. Okay, and then also we have by this definitions in this way that's the boundary operators constructed in this way we can derive these relations. So it's like this. So that this C n minus 1 C n and the C n minus 2 we have this guy delta t, and this is delta t minus 1. So the composition of these two guys becomes 0. So 0 arrow. These guys are, of course, Banach spaces. Banach space. So they are 0 means just the vector space which consists only with 0. And this, if this chain satisfies these relations, we usually use just delta square equals 0. Then it is called a chain complex. So like this, chain complex. And yeah, and then with this chain complex, we can, we can define the homology. Say this is a chain complex, so we have these guys. Then this means that if you think about focus on this part CT, then this outgoing CT can give us the kernel. So kernel is kernel is kernel of this guy is there is a 0. So all the elements of CT which is going to 0, and the set is kernel, and it's of course a subset of CTC. Also, this T plus 1 makes some image of the, I'm sorry, delta T plus 1. So this is just an image, because of these three guys call that this is 0. So 0 is this is kernel, and the image must be inside this kernel, because of the combination of these guys becomes 0. So which means image of these guys is here, should be inside of the kernel. A kernel is a set which goes to 0, 0. So we have this relation. Okay. Now, because these guys can be observed as the groups, abelian groups. This is abelian group is a commutative group, which is A B equal B satisfies this guy's commutativity, and the abelian group. And we have two. So this is a subgroup of these guys, and this is a subgroup of this guy. So we can define these relations. Two abelian groups, which is one is the other one subset. Then in this case, we can make a quotient subgroup. This is also the abelian group, and this is called the homotopy group, and it represents the difficulty of some abstract of this chain complex. Okay. All right. So now we use this homology. So how to use this? We have the plan. So this homology groups HCT is expected to quantify structural inconsistency or redundance. Redundance with spell is different, but redundance within the probabilistic evolutions. And it is also taught to detect T cycles. T cycles, I need to explain, but it's going to 0. So it's a kind of kernel or the dependencies part of the given context in the filtration that cannot be resolved by the T plus 1 step behavior. So the previous part step behavior. So that by the future, there's something we cannot specify by the past or the in this way the futures phenomena, this kind of things. I will explain concretely later. I hope I can explain. Okay, the next one is that these probabilistic homology class express how information fails to glue perfectly across context. So it means in this situation you see that we have some well, okay, see more concretely. We have this kind of space, right? And then this is 0 here, and here is kernel, and the image is mapped into these guys. So here are two regions. I'm sorry. Here are two regions. So this inside region and the outside. So within a kernel, but so the point is that if this red part and the green part coincides, so then it's perfect. Everything can be explained by the consistently. But if this red part, so which is or I said that red part is vanishing, then everything is consistent. But if there is an area of the this red part specifies, then there is some something which are not explained by these guys. Okay, so this red part is cannot be explained by the next steps or the futures phenomena. So it is some difficulty there is in a categorical sense or the geometric sense. Okay. In other words, it provides an algebraic measure of uncertainty. So I think some uncertainty comes from this red part. Okay, this is the idea. Usually, the uncertainty comes from the variance or the entropy or those stuff. But this time, we find we define some geometric way the source of uncertainty. Okay, now we step further by more concrete explanation of the sigma filtrations, which is a degree filtration. This is the final part. So we have just some small, very well-known functions, beta functions. So this is just we just defined these Bn functions with the parameters alpha 0 to alpha n, and the x is a vector x0 xn, which is inside simplex of the. So this is a convex set. So the sum of these guys is 1, and they like this, and then we define 10, equation 10, and we define another equation Bn. This is called the multivariate beta function, and this is gamma functions, and the ratio of these two guys is called a multivariate beta functions. Simple beta function is just n equal when the n equal 2 case. N equal 1 case, 2, 1. But we have the general case, n case. And we have these equations. This is well known, b sub n alpha. So this multivariate beta function can be represented, this integral representations. And so they just integrate over the whole delta n. We can have these guys. Okay. So from here we can make some kernel for the probability densities like this. So this is a kernel for the point x. Then some of them is 1, of course, by these equations. So this would be the candidate, very good candidate of the density. And we will use these guys here anyway. But so the Dirichlet distribution is originally defined by like this, where the GI is a gamma distributions, and then we have these guys Fy. Each Fy is the member of the vector F. Then F is called the another has Dirichlet distributions with parameter alpha. These guys, and yes. So yes, this is what I told already. It become a density functions. Okay. So we introduce a probability measure to the topological space, this guy, or the measurable space, this guy. Because of the remaining part, we missed when defined the delta, sigma filtrations. All we need is, I'm sorry to say, go back. These guys, called blue one is not specified, but others are already specified. So the all remaining, all we need to specify is this probability measures for each time t with context c. We need to define these guys, and we will we will specify this probability measure with a Dirichlet filtration. I'm sorry, Dirichlet measure or Dirichlet functions. Okay, so that is what we did. Okay, here. No, not here. So this mu a is a probability measure. Just I explained, which was missed, and defined with guide. Remember, this is a probability density functions, and with some Euclidean usual Lebesgue measures, Lebesgue integral. We have for each a is a measurable set of the convex sets delta n. We introduce by using these guys. We can introduce a probability measure. So now the point is a U alpha, where alpha is this guy n plus one parameters, n plus one parameters, positive or positive. Okay. So now, before, so we want to use that guys in the sigma filtrations, but this not so concise. I'm sorry, I can't provide some concise introduction for that. But using the other stuff, I need some other stuff, which is Diri. This is a category of Dirichlet parameters. So we concentrate on the parameter alpha, which is n plus one sequence of the positive numbers, and then with these guys, and this, of course, this is n and alpha. Then we can define the probability space. This guy p and alpha, which is defined like this. So the first one, delta n, is okay, and the beta is I don't know. This red part is not good, but anyway, the first two is already defined. It's very naturally defined. So we missed these guys, but this guy now used to it was a p cn or something, but we now defined these guys with mu alpha, which is derived from the Dirichlet distribution. This is Dirichlet distribution with a parameter alpha. Okay, and so depending on this alpha, we have the probability space. So even with the same measurable space, delta n and beta delta n, we can have many thought of the probability space by changing this parameter alpha. And mu alpha specifies a probability measure according to the Dirichlet distribution. And so all this pair in alphas, we have these guys. This is the object of the new category DD, and the arrows in between these guys is just null preserving maps in between these two probability spaces we just defined here. Okay, and then this correspondence P, which would be becomes a functor, is naturally defined. And using this functor P, we define the Dirichlet functor. This is final one. And this is a filtration. This is filtrations. Will be filtrations, Dirichlet filtrations. And P is just from the DD. This is a pair of the object. It was a pair of the N and the alpha. And we have this guys here, the delta N and the beta delta N and the mu alpha. Is mapped by P, and D is a Dirichlet functor I just showed defined. So with the convex we have because this part is T C, but so each ETC has we have the delta and so the with this D, we have the Dirichlet object, which is this pair of the N alpha. And then, also there's a Fagetful functor here, and this is a standard realization, and this is just a bare, Borel functor. And making this commute, we call this Dirichlet filtrations. So Dirichlet filtration is the T filtration or the sigma filtration, but especially define their probability measure by the Dirichlet distributions. Okay, so something I can mention is for Dirichlet parameters, Dirichlet parameters in this case is the n+1 length sequence of the positive numbers. But for if we have the point at TC, we need this guy. Sorry, this guy's. Then so this is if we have the Dirichlet functor D, which assigns the T in the context C to the pair of the time T with parameter alpha. Then the previous one. Okay, so the next one would be like this T+1 beta, but the beta is this is a degeneracy map. So the decreasing one dimensions by this is a dual of the little delta, and then becomes alpha. So this is a constraint, but we have some we have some freedom, and it's so the beta k-1 beta k you can take any element any numbers values as long as it satisfies these guys. Of course, each beta ki -1 beta k, these are positive, but some of them should be the alpha k. But we have freedoms. So this is a parameter freedom. And then this is a parameter uncertainty for the future. But we have the contextual uncertainty already, we saw it, So now we can, divide our uncertainty into two parts. First one is a contextual uncertainty, which comes from the multiple past. And this is for the past. For the future, we have the parameter uncertainty. This comes from the Dirichlet parameters. So we have two sources of uncertainty in this model. Now, the last topic is how to interpret the Bayesian update. Because it is well known that the Dirichlet distribution is a conjugate prior in the Bayesian sense. So we can use this. So for in order to do that, we need to see the multi-dominant distributions. So Tako Bunpu, MTQ, and the Q is the parameters, and then we have these are defined like this. This is a multinomial distributions, and here this Q is parameters, and is an element of the delta T complex. And then but this Q itself is a random variable because this is Bayesian. Okay, and so and having a uniform distributions, so it's like this. So in this case, this Q is element of the probability space defined like this. So we are now, because this is Bayesian, the parameter is also the random variables. Since that random variables lives in this probability space. So we moving these guys in this by moving these guys, we update the prior posterior probability distributions. And okay, so I don't go into the detail, but we can think about this update. Okay, if we observe something k at time t sub c, the context c, then this is the outcome. Then we update the parameter of the Dirichlet distribution. We can update because of the Dirichlet distribution is a conjugate prior. So we can make because we observe k, so we just add 1 to the alpha k+1, then mixing alpha dash. This is a new parameter list. And using this new parameter list, we can update the Dirichlet functor itself. So this is the interpretation of the Bayesian update in our model. Okay. All right. So we just conclude the talk. We made a model in which the present is formed by the synthesis of the multiple past. And then to make it possible, we introduced the concept of time in the context and the category sigma as a time domain of our generalized filtration. And we developed the homological theory of sigma filtrations, defining boundary operators from our conditional expectations. And we made an interpretation of the homology of sigma filtrations as an algebraic measure of the informal inconsistent. Okay. And also, okay. And then in order to make sigma filtrations more concrete, we equipped each probability space with a Dirichlet distribution and introduced the concept of Dirichlet functor for assigning consistent Dirichlet parameters to the probability spaces. We also saw two types of uncertainty in this model. One is a contextual uncertainty of past and parameter uncertainty for future. We updated the Dirichlet functor by using the Bayesian method. It may relate to some the financial concepts. Okay. We have some further research topics. We explore the homological and topological invariance of sigma filtrations, connecting to the classical concepts in stochastic calculus and financial theory, such as martingales and non-arbitrage properties. Actually, if I have time, I will explain this martingales part. The non-arbitrage properties are still ongoing research now. And we want to extend the theory of synthetic filtrations to continuous time and extrapolate its relationship with classical stochastic processes. The difficult part I thought was the continuous time, because our model is a discrete time, because of delta n, so the t is moving still the integers. But recently, I realized that there is a way of introducing a continuous time. If I have time, I will explain some about that. And finally, I will find applications in finance and economics where the information often arrives in context-sensitive and nonlinear ways. This is very important as an applications. The details of today's talk is available at this archive. Thank you very much, and I stop this at this point. Okay.